Hi again, everyone. We're going to be picking up where we left off. So just at the end of alkanes, where every carbon is bonded to another carbon, as well as 2 or 3 hydrogens, and picking up on alkenes. So an alkene is a unsaturated hydrocarbon. So we said a saturated hydrocarbon was one where every carbon is bonded to there's only single bonds with other carbons and is completely filled otherwise with hydrogens. So with alkenes, we have at least one carbon-carbon double bond. General formula for one double bond, so this is going to change depending on how many double bonds are in the molecule. We'll talk about polyenes in a second. But for just one, for every n carbons, there are 2n hydrogens. So if we draw just kind of a generic organic molecule, what we're looking at is doing a double bond. Yikes, that looks like a triple bond now, doesn't it? Let's try that one again. Okay, a double bond on one of the bonds between the two carbons. So how are we going to number this one? As opposed to before where it mattered about the side groups, this double bond now becomes the important feature that's going to define it as an alkene. So it takes the lowest number possible. So on this one, we could either number it 1, 2, 3, 4, 5, 6, or we could number it 1, 2, 3, 4, 5, 6. So this would either be a, let's see, that double bond started on number 2, so that would be a 2 hexene, or it would be a 5 hexene if we did it the other way, or 4 hexene if we did it the other way. Obviously 2 is a lower number than 4, so 2 gets the nod on this. So we would number it from left to right in this case. Okay, and again, you see that we still have the same roots for the number of carbons, so it's still a hex something. We're just changing the back part to say ene instead of ane. Okay, the carbons at the double bond are in a sp2 hybridization. So remember where we had our sp3 carbons, so we have 4 bonds, they're all equally spaced. Now we're going to replace that with a carbon with a double bond on it, and the 2 other bonds are all going to be equally spaced at 120 degrees from each other and flat in a plane. Okay. The double bond is more reactive than a single bond, just because we do have that concentration of electronic charge that can potentially react with something else, where the electron density in the single carbon-carbon bonds or in the single carbon-hydrogen bond is really located between those 2 nuclei. This is a little bit more diffuse, and so there's a more potential for a different molecule to come in and interact with it. Okay, so naming alkanes, we've already seen a small example there, where we're just going to replace the ane with an ene, so hexane becomes hexene if it has a double bond in it. We're always going to look for the chain that has the longest chain that includes the double bonds. So if there's a longer chain that does not include the double bond, that gets broken up into different side chains. We've already mentioned that we number the atoms on the parent chain so that the double bond gets the lowest possible number. And otherwise, everything works the same as per alkane. Okay, so there's a few examples on the screen there and on your page. So go ahead and give those a try. And again, I'll talk our way through how we're going to decide what they should be called. Okay, so this first one, we see it has a double bond in it, and that's going to get the lowest number possible. So we just start counting up carbons from that side. So let's say 1, 2, 3, 4, 5, 6, 7. Okay, so we should say that it's a hept, and it's got a double bond, so we can say it's a heptene. That heptene, the double bond is on the second carbon, so the second one is the one starting it. So we always take, again, the lowest number. So it would be a 2-heptene, and there are 2 side groups on it, both methyl groups, and those are on carbons 5 and 6 of the parent chain. So this would be a 5, 6, I won't fit there, but we'll do it below, dimethyl. 2-heptene, okay? So 5,6 dimethyl 2-heptene would be the correct full name for that molecule. All right, so looking at example number 2 in the middle of your page, so we can see we got 1, 2, 3, 4 up to the top, or 1, 2, 3, 4, 5 if we go along the bottom. But that chain along the bottom doesn't include the double bonds, so we can't include that as the parent chain. So what we have instead, get rid of that, stop it. So what we have instead is to start where the double bond is as carbon 1, 2, 3, 4. So this is a butene, and there's a 1, 2 carbons, so that's an ethyl group that's on the number 2 carbon. So it would be a 2-ethyl, 1 butene. Okay. And here in this final example, the only kind of tricky thing is that we've lodged 2 of the carbons in the middle of the chain into a shortened form. So we'll just count that twice. We have 1, 2, 3, 4, 5. So this is a pentene. And the double bond is on the number 1 carbon. So it's a 1-pentene. Okay. All right. So that's the naming of the simple single double bond on a carbon chain. But of course, we're not limited to only having 1. So when we said it was an unsaturated or a saturated hydrocarbon, we're restricting ourselves to say that every single carbon on there is only single bonds to other carbons or to hydrogens. As soon as we say that it's unsaturated, there's a possibility that there are more than 1 double bond on it. And those we call polyenes. So poly just meaning many, and of course the ene part is just the suffix that we're using for these. So dienes, trienes, 4, again, we're using the Greek roots, so this would be tetraene, but polyene is fine for the most part, okay? So what would this look like, again, as kind of a dummy example? So let's just draw something out here. And we'll put a couple of double bonds on here. And to name this guy, again, we're going to take 1, 2, 3, 4, 5. So this is would be a pentene if there was only 1, but because there are 2 and we want to say how many there are in the name itself, this is going to be a pentadiene. And we also number exactly where they're going to be found. So this is a 1, 3, 1, 2, 3, 4, 5. So this is a 1, 3 pentadiene. Of course, there's other ways that we could make a 1, 3 pentadiene, right? So let's start it off the same way. And so now we've got still 1 and 3 have double bonds on it. But if we put the other atom going the other direction, so we have 1, 2, 3, 4, 5 carbons still. This molecule is now different than the one that we just drew. But if we were going to try and name it, it would still be a 1, 3 pentadiene. But just based on the shape of it, we could expect things like boiling point, melting point, some of its reactivity to also be different. Why don't these convert back and forth to each other? So as soon as, like we said before, if there's a single bond, just like a single nail holding 2 boards together, the 2 boards can swing around just on that one point of rotation, that one axis of rotation through the nail. As soon as we stick a second nail in that board, you can't swing it anymore. this double bond is like that second nail in the board that's preventing, say, this bond from rotating around. So as soon as we decide which direction this is going to lie in, whether it's going, say, towards the rest of the molecule or away from it, that's going to change the molecule and how it behaves. So this is a different kind of isomerism called geometric isomerism. And we want to define, of course, what it is. So we use the prefixes cis and trans to indicate the structure. So I think I've lost our screen, which is too bad. So the first example that we had there, because the large groups, are we back? Maybe not quite. The large groups are on opposite sides of the double bond. So this would be a trans conformation. And if the largest groups are on the same side of the double bond, this would be a cis conformation. So I don't know why we're not seeing that on the screen, but maybe we'll just give it a second. So we can do this with just an ethene. And so like a dichloroethene, if the chlorines are on opposite sides from each other, then, oh, it's slowly catching up to us. Okay, so this would be a trans dichloroethene. And if we put the chlorines on the same side to each other, we're catching up now, okay. On the same side to each other, this would be our cis dichloroethene, okay? So this would be a 1,2 cis 1,2 dichloroethene. Okay, hopefully it sticks with us from now on. All right. Okay, so hydrogenation. You would have heard this maybe when we're thinking about like margarines or trans fats. Why are we calling it trans fats? It's because there is this trans group in it, in an oil that wasn't completely hydrogenated. So hydrogenation, usually we're looking at some kind of flat surface where we can locate hydrogen gas. So there's going to be, say, like some atoms on the surface that just interact quite weakly with these hydrogens, but keep it more or less in place. Okay, so when our carbon-carbon double bond comes along, and remember this is a flat molecule because both of those carbons are in a plane with each other and lie on a plane. So it can more or less be like a flat thing coming in and laying on top of these two hydrogens. So when we get something like that, the electron density that would have been bonding these double carbons or the hydrogens together, it goes out and finds these hydrogens that have a slight positive dipole on it. And what we end up with are two new bonds being made with those two hydrogens, okay? And so now we take our ethene and we end up with an ethane. Okay, and we can do this for any kind of size molecule. So usually what you would look at is to take quite a long oil, like a plant oil or a vegetable oil, hydrogenate it so that it becomes a solid. So that's the idea behind margarine, really. Okay, and that's alkenes. We'll push on into alkynes. So alkynes, the rules really don't change. It's just we're looking at a triple bond instead of a double bond. So an alkyne would be what you would fill in that block of text there. Alkyne is an unsaturated hydrocarbon containing at least one carbon-carbon triple bond. The general formula, again, this is only the case where there's one triple bond there, but it would be for any n carbons, it would be 2n minus 2 hydrogens now, because we're taking, say, carbon and carbon with a triple bond between them. Now we're losing all of the carbons on this two, or the hydrogens on those two carbons, and working it out to the end. Okay. So these are, again, more reactive than an alkene. An ethyne, where do we see that? Welding, actually, a lot as a welding gas. And you'll notice also that the carbons involved in these are sp2. sp2, okay, sp2 hybridized, and are linear in conformation, okay? So when we look at them just in a drawn molecule, we can't rely on looking for where the molecule bends anymore for where the carbons are. We just have to recognize that when the number of bonds change, or just after one kind of length of the bonding, that's where we're going to find a carbon. Okay. So we can look at the first example. Again, all of the rules are going to be the same here. So we're just replacing ane or ene with eine. And on that first example, so we have 1, 2, 3, 4, 5, 6. So this will be a hexyne. And if we counted from left to right, we would have it at a longer number than if we count from right to left. So that will be a 2-hexyne. Okay, if we go over to our next example, so this hockey stick looking thing, and we count that, so it'll be 1, 2, 3, 4, 5 carbons in total. The triple bonds are on carbon 1 and on carbon 4. So we'll call this a 1,4 penta, and here we put in di, and ended off with the yne suffix. So 1,4 pentadiene. Okay. In the last example, there's a double bonded group and a triple bond. So of course this isn't a diene or a diene, but the triple bond takes priority over the double bond, and that's, you're going to see that as a trend when we go through the functional groups. Some do take priority over others. So the yne is still going to take the name, the full suffix for the whole name, and it's going to take priority of position. So that still gets to be number 1, 2, 3, 4, 5 as we go through. So this is going to be a 4 pent. So for the 5, we get the pent part. And then we'll write an ene and a 1 ine. Okay. We can also write it as a pent 4 ene 1 ine. But I don't find that as aesthetically pleasing, so I don't tend to do that. So we just want to be as clear as we can be about what functional group is at what position. So either 4-pentene 1 ine or pent-4-ene 1 ine is both are acceptable. Okay, and the last thing we're going to touch on quite quickly is alicyclic hydrocarbons. So these are our cyclic hydrocarbons that aren't aromatic. They're not double bonded in such a way like we'll talk about very soon with benzene. So these ones are all single bonded carbons together, but now they're bonded so that they're in a ring. To show that, we just add cyclo as a prefix. So get out of here. Okay. So the first example would be cyclo propane. And if we work it our way through, we have cyclo for it's a ring conformation. The prop, there's 3 carbons in a row. And the ane saying that they're all single bonded. The second one, you might be able to guess, is cyclobutane. The third one, cyclopentane, and this will carry on. you'll also see that the angle between the carbons that a cyclopropane makes at 60 degrees is a lot more constrained than a carbon likes to be when it's in an sp3 conformation or a hybridization state at 109.5 degrees. So that puts some strain on the bond, and it makes the molecule itself a lot more reactive. Same thing, but to a lesser degree with the cyclobutane. Now it's at 90 degrees, so we're getting a little bit closer. Cyclopentane, of course, is a little bit closer again. But at cyclohexane, we get very close to where it's already quite comfortable. So that's why we tend to see carbons form that cyclohexane a lot more often than the other options. Just because it's a lot more stable, because the carbons are already at an angle where they're reasonably comfortable. So even though it's often drawn flat like that on the page, I think by now you can guess that it's not actually flat, because again, if we were looking at the hydrogens being drawn off of each of these bonds, I'm not going to go around and draw all the hydrogens, but you can imagine that they're all there. One of these can be straight, but something else has to go on here. So either these bonds are coming out the page at us or back into the page. And so this gives up two different conformations that this cyclohexane can take. One is called the boat. So we'll try that one first. So a boat is where two of the peaks would be on the same side. And if we draw it looking at it kind of from the side, it would look like a boat, okay? So this is still our 1, 2, 3, 4, 5, 6 carbons. They're just arranged in such a way, and we can draw the hydrogens kind of, so you can imagine where those are sitting, coming off of all of these as well, okay? And it looks a lot like a boat. And the other one, the chair conformation, this is where these two peaks would be facing in opposite directions. So we have the point coming down, going over, and then coming up into the other point, okay? And this is again a cyclohexane, just a different conformation. So this would be the chair conformation of that one, because again, it looks a little bit like a chair. Okay, there's a guy who's got a little table with his, I don't know, we'll call it Friday, little glass with an umbrella in it. Okay, so that's where we're going to leave it off, and we'll talk about the aromatics next time. So thanks for watching as usual, and we'll pick it up on the next video.